So Rutherford's discovery gives us a model of the atom as a mechanical system. In fact, it should make physicists very happy because it is a unifying model. We have a recurrence of a model we've already solved. This is a universal pattern that usually suggests something very deep. We've seen that before. We have a central nucleus surrounded by orbiting electrons, much in the way that in the solar system we have a central star or surrounded by orbiting planets. The structure is familiar, understood, and we know a lot about its phenomena. What is the problem? Well, the problem is that in the context of an atom, it doesn't work. The model is fatally flawed, and Rutherford knows this, and everybody knows this very rapidly. What's the problem? Well, the problem, as we noted, is that the electrons that are orbiting the nucleus are charged particles. Charged particles create electric fields. Charged particles that are moving with changing velocities are accelerating, create changing electric fields, which create changing magnetic fields. In other words, an accelerating charge leads to electromagnetic radiation. Well, fine, we wanted these oscillating atoms to generate radiation. This is what we saw. Atoms radiate. But atoms would be radiating all the time because an electron would always be orbiting. The electrons are always in motion around the nucleus. Furthermore, if one takes the simplest example of a hydrogen atom, a nucleus surrounded by one atom, and the atom is orbiting, say in a circular orbit around the nucleus, one can easily compute the rate at which electromagnetic radiation is produced. Well, fine, so atoms are radiating. Conservation of energy is the issue here. As the atom radiates away electromagnetic energy, the atom must lose energy. Where is that energy coming from? You can do the calculation. It's clear that where the energy is coming from is from the orbital motion of the electron. The electron, well, it's not quite slowing down. As we know, what happens when an orbiting object loses energy, it becomes, descends to lower, more negative energy. More negative energy means smaller values of R. Remember, the total negative energy of an orbiting object is minus gm over 2r in the case of gravitation, and Coulomb's law is very analogous to Newton's law. And so when the electron loses energy, it actually spirals closer to the nucleus. And because A is now smaller, P is now smaller, it actually orbits more rapidly near to the nucleus, radiating more. And so an atom is an unstable system in that if you start an electron orbiting around a nucleus, it will very rapidly radiate all its energy, and the electron will spiral down inside the nucleus, and you can calculate how long an atom would last, and the answer is fractions of a second. This is a problem because clearly atoms exist, they are stable, they do not radiate themselves to smithereens, and now we have a real problem. There is no answer within Newtonian physics and everything we know about electromagnetism. There is no way to resolve this problem. Related to this, if we understand that the oscillatory motion of the electrons is responsible for atoms radiating, then we'd expect the frequency with which an atom radiates to be the frequency of the electron's motion. That's only natural. But the frequency with which an electron orbits is known to us. It follows Kepler's law that we've become familiar with. And if as an electron orbits at different values of A, it will radiate with different frequencies P. But we only detect that atoms seem only to radiate or only to absorb radiation at discrete, specific values of P. It's as if there were only discrete, specific values of A at which an electron were allowed to orbit. So maybe an electron is on rails in some sense as it orbits the nucleus. It's not allowed to orbit, unlike planets. They don't orbit through empty space. There's some internal structure that constrains the electrons to only orbit at specific values of A. These are the kinds of ideas that are floating around turn of the 20th century physics. At the same time that the leading minds in physics are puzzled by this bizarre behavior of atoms and their spectra, other sort of chinks, other problems, other experimental puzzles are discovered that again cannot be understood by the Newtonian physics with all of the additional 2.5 centuries of details that people have been filling in. One involves the behavior of light. So remember, Newton had conjectured that light was a stream of particles, and there were green light particles and red light particles and yellow light particles. And Young had definitively shown that Newton was wrong by observing that light waves exhibit interference. You can shine two light beams on some detector, and under suitable circumstances there will be less light at the detector than there would be with each of the two light beams separately. Particle beams don't subtract in that way. Wave phenomena exhibit interference. So we definitively know that light is a wave. But under some circumstances, in particular in the details of the spectrum of a black body as observed by Planck at the turn of the century, and 5 years later in a phenomenon known as the photoelectric effect that we won't get into the details of. It is discovered that under some circumstances, a beam of monochromatic light, light of a given color, behaves as though it were a stream of particles. These particles are given the name photons or light quanta. This is the quantum theory of light because each of these particles carries a quantity, a quantum, a discrete amount of energy. And if the color of the light determines a frequency f, then the energy of each of these photons, as these light quanta are called, they're called photons because they are light particles, and they move, of course, at the speed of light, and each of these photons carries an energy that is determined by its frequency completely, and the constant of proportionality is this number that is called h. It's called Planck's constant. As I said, it was first discovered in the details of the blackbody spectrum by Max Planck, but in the context of the photoelectric effect, it is determined that under some circumstances, the interaction between a beam of light and some material occurs as though the material is absorbing light, not continuously as the wave transfers energy continuously into the material, but as though discrete amounts of energy are being taken out of the light beam and into the material, and these discrete amounts of energy are proportional to the frequency, not the intensity of a light beam. How much energy the light beam carries, as determined by its intensity, that determines how many photons per unit time, per unit area. The flux of photons in the beam determines its intensity, but the energy of each photon is determined by its frequency. High frequency, short wavelength light involves photons of higher energy. This is a puzzle. Light is a wave, but sometimes light is a particle. Aha! Even more confusing development occurs about 20 years later when American physicists Davison and Germer show that under suitable circumstances, electrons, certainly particles, localized objects with a particular position in space and a mass, electrons sometimes behave as though they were waves. In other words, sometimes you can shine two beams of electrons on a detector and find less electrons in some places and more in others than you would with either of the two beams on its own. So electrons, under some circumstances, behave as waves. Light, which is a wave, under some circumstances, behaves as a particle. Newtonian physics has no room for these, any of these dualities, and the theory that resolves them all, a beautiful and to this day rather puzzling theory called quantum mechanics, requires us to completely rearrange our understanding of the universe at every level, and yet, of course, does not invalidate all of Newton's results about the motions of the planets, because, like all good physical theories, it does not invalidate what worked in the previous theory. But at a philosophical intrinsic level, we have to redo all of our understanding of science. We are not going to do a thorough job of understanding quantum mechanics. That would take more than the entire length of this course, I fear. But let's see some of the outcomes, some of the conclusions that people draw. Basically, what we learned, what quantum mechanics teaches us, is that particles, be they photons, electrons, protons, whatever it is that they are really the dynamics of particles, the mathematical, physical description of the physical behavior of particles is encoded in an object called a wave function, an object which obeys equations that are mathematically, formally, very similar to the equations that describe the propagation, say, of a light beam, in many senses. So there's this function which exists like the electric field at every point in space at every time, and this wave function of an electron, say, somehow describes the state of the motion of the electron. In what way does it describe it? Well, one way to understand it is that the position, at any position in space at any given time, the value of this wave function, or some property of it, the square of its value if you want to be technical, predicts the probability of finding the particle there. So if you have an electron and you know its wave function, you can predict the probability with which, if you try to find the electron at any point in space, you'll figure out the probability to find it here or there or elsewhere. But only the probability. Physics is intrinsically probabilistic. It's not that the wave function reflects our lack of knowledge about the system. No, knowing the wave function is a complete description of everything there is to know about this electron. And yet, if you try to predict the result of an experiment, say, trying to find the position of an electron, trying to find an electron at some position in space, that can only be described probabilistically. There are only probabilistic predictions. This wave function behaves like a wave. It has a wavelength and a frequency. Its frequency is related to the energy of the particle. Its wavelength is related to the momentum of the particle. And the relation is that the wavelength is this infamous constant of Planck's divided by the momentum. So high momentum particles, something moving fast, has small values of the momentum. Remember that h is a very small number. So for example, even if I am moving very slowly, my mass is so large that when you remember that p is m times v, no matter how small my velocity, my macroscopically huge mass means that my wavelength, h divided by mv, is very, very small indeed, smaller than an atomic nucleus. You will not detect the quantum effects of my wavelength or the fact that there is an issue of probabilistic limitations on predicting where I am here. And that is quite definite. Classical physics describes very well large objects whose masses and energies and momenta relative to the Planck constant are very large. When does a wave description describe light? Well, we said that a light beam is a stream of photons. The energy of a photon was Planck's constant times the frequency. If there is a high energy flux, high intensity beam, that means there are lots and lots and lots of photons. Under those circumstances, the discreteness, the fact that the energy is being carried in these small discrete packages, is irrelevant if you have high intensity light. The energy within each photon is small compared to the actual energy carried by the beam. But beams of very small numbers of photons, there you will have quantum behavior of light, and very small microscopic particles will exhibit these strange quantum behaviors. What are the consequences of this? Well, as I said, I'm not going to teach a class in quantum mechanics. There are very good classes that other people teach on quantum mechanics. How does this resolve the issue of the structure of an atom in spectra? Well, see, the mathematical description of the wave function, the equation that determines the wave function of an electron and atom, is at least formally very similar to the equation that determines, say, the waves that can propagate along a string. And remember, a string oscillated at particular frequencies. In similar way, it turns out that the frequencies with which this wave function oscillates within an atom, it's a three-dimensional version of the same problem, are indeed discretized. If you solve the problem for the hydrogen atom, which is quite simple, you find that the energy levels, the energies, the frequencies of these wave functions for the hydrogen atom are proportional. There are a whole slew of allowed discrete energy levels, and the energies are given by some constant called the Rydberg constant. It is not the same old Kepler constant that we had before, nothing to do with the solar system. Divided by n squared, the energies are all negative. These electrons are bound. This is set up so an electron at infinity has energy 0, and an electron can have energy minus k over 4, minus k over 9, etc. Larger values of n involve higher and higher values of the energy, closer and closer to 0. So all the values are negative. The most negative value is negative k, and then negative k over 4, etc., all the way closer and closer to 0. Now, so this tells us why an electron does not spiral into the nucleus. Once it gets to what is called the ground state, the lowest energy state, energy negative k, that's the lowest energy the electron can have. It can no longer radiate. In fact, at any of these energy levels, an electron is not able to radiate because these are those rails, the sort of fake rails. They're not really rails on which particles move. They're wave manifestations of a similar idea. And when an electron is in a particular state, it does not radiate. To radiate, conserving energy. The process by which an atom interacts with radiation, it turns out, is that a single atom either emits or absorbs a single photon. So that, for example, an atom in an energy level indicated by the number n can jump to an energy level m. And if, for example, m is a larger number than n, so that this energy is lower than that energy, then the total change in energy is determined by these two numbers. And if this is going to occur by the emission or absorption of a single photon, then the energy carried away by that photon, by conservation of energy, should be given by this change in the energy of the atom. The change in the energy of the atom determines, therefore, the energy of a photon, and hence the frequency. So that what we saw when we saw the selective absorption of particular wavelengths of light, particular frequencies of light, by specific species of atoms, was we were measuring the spectrum of energy levels and the differences between the various energy levels, so that absorption of one photon allowed an atom to jump up a particular discrete amount as determined by the energy spectrum of that particular atom. Let's see a sort of animation that explains something about how this might work. Now, I'm not going to claim that I just explained quantum physics so that we all understand it. That, as I said, is sadly beyond the scope of this class. We're going to formulate and then use heavily some of the consequences of quantum mechanics, and I wanted to at least give you a flavor of where it comes from. Perhaps this animation will slightly help us. So what we have here is a box in which we have hydrogen atom, or a bunch of hydrogen atoms, and what we are going to do is we are going to be shining white light at them, and the white light is depicted as a stream of particles, but you can imagine pulses of light of various colors, because we know that white light contains all colors, and as we shine white light at this atom, we notice, as we are aware, that the atom absorbs and then re-emits light, not at all frequencies, but only at particular frequencies. We see here that there's a particular wavelength in the ultraviolet, and if we give it enough time, there'll be a particular wavelength in red light at which this atom is emitting. Well, how do we explain this, you ask? Well, here are some possible theoretical models, and let's see what they would predict. So, Thomson's model, known as the plum pudding, has light negatively charged electron moving within some complicated matrix of distributed positive charge, and presumably the motion of the electron has resonant frequencies, just as the string that was excited by the bow had resonant frequencies, and when light shines upon it, only if light hits it with the appropriate resonant frequency, the electron will oscillate and then re-emit the light at the frequency with which it is oscillating. And this again explains why an atom, you could attempt to construct such a model, and this would explain why an atom would absorb and emit radiation at discrete spectra if you could construct a suitable mechanical model of the interior of the atom. Unfortunately, of course, we know that this was destroyed by Rutherford, who discovered that in fact the positive charge in the atom is not distributed, it is concentrated in a nucleus, there's an electron there. The only way for the electron not to fall under the force of its electric attraction to the nucleus is for the electron to orbit, and as we know, what happens is the electron radiates, and so the prediction of the Rutherford Keplerian atom is somewhat disturbing. Kaboom! The atom decays within fractions of a second and does not survive. The slightly more sophisticated, somewhat quantum version is the version of Bohr. The Bohr atom, this is some quasi-quantum description. Again, the electron can exist at a variety of energy levels. Bohr imagined them as literally rails, or figuratively, rails around the atom, orbitals, which the electron could occupy. We see the electron in its ground state, n equals 1, the most negative energy that an electron can have, and therefore it's not going to radiate. But if a light quantum with an energy whose energy is, as determined by its frequency, is precisely the difference between this energy level and this energy level, so minus k, the difference between minus k and minus k over 4, or 3k over 4, if you find a photon with precisely that frequency, that photon can be absorbed, the electron will then jump from this orbital to that orbital, essentially instantaneously annihilating the photon, and then after a while, for reasons that are hard to calculate in this model, it will re-emit the photon, jumping back down to the ground state, and this is indeed what we see happening. We see the electron periodically bouncing up to higher energy levels. Let me perhaps slow the simulation down. And you see that when a photon of a suitable wavelength comes along, it gets absorbed, bouncing the electron to some higher orbital, and then the electron decays back to the ground state by emitting photons only of specific frequencies. So this high energy photon corresponds to this large energy difference, the difference between n equals 1 and n equals 2, and these lower energy photons correspond to these smaller smaller energy differences between the higher excited states. And of course, if a photon came along with sufficient amounts of energy, it could knock the electron completely out of the atom, so there will be a maximum energy above maximum frequency. If you have light with frequency above that, it can just knock the electron completely out of the atom and ionize it. And we'll see that that too is indeed true. A more sophisticated quantum mechanical picture, the Schrödinger atom, the electron is described by this wave function. This is some representation of the wave function. The probability of the electron being at any particular position is how brightly blue the screen is at that point, and emission or absorption of a photon can excite the electron from one state of the atom of its wave function to a different wave function, and then it decays back into the ground state. For us, the differences between these are a little bit too subtle for the level of distinction that we are making. What is the point? The point is that when you apply the Schrödinger model with some additional things that we have learned since, you can in fact predict how much of the light the hydrogen atom, what is the probability at a given frequency that the hydrogen atom will absorb a photon, how long it will survive in the excited state before decaying back to the ground state, if it's at some excited state, what frequencies and what energy, what sequence of energy levels will it occupy along its way back down to the ground state. All of these can be computed and agree with experiment. So the theory, while very difficult to understand, and not trivial to do calculations in, is extremely successful in making experimental prediction. So we claim we understand quantum mechanics rather well. So I didn't completely clarify quantum mechanics. In many philosophical senses, it's still a puzzle today. I hope what I managed to get across is the fact that we do understand very well how to use the theory to compute quantities of physical interest and make predictions, that it underlies all of the technology that drives our modern world, from semiconductors to lasers to I don't know what else. And it allows us to understand how all these things work. It does produce an understanding of atomic spectra and an understanding of the structure of an atom, so that the nuclear atom is in fact a consistent structure within quantum mechanics. That's very important. The other thing that's important to us is that it produces, as sort of a byproduct, this exciting result known as the Pauli exclusion principle. And this will be very important to us in some aspects of what comes next. The Pauli exclusion principle applies to particles such as electrons or hydrogen nuclei, as we shall see, or some other particles we will meet. Those particles are called fermions, and particles that obey the Pauli exclusion principle are unfriendly. Technically, what this means is that at most 2 electrons can occupy a given state. If you want to get really fancy, the answer is really at most 1 electron can occupy a given state, but electrons have some internal degree of freedom called spin that has 2 possible values. What this means is, for example, when you build a hydrogen atom, it has 1 electron, and that electron likes to be in the ground state. When you build, say, a lithium atom, there are 3 electrons. They can't all 3 be in the ground state. 2 can be in the ground state, and then the ground state is full. We learned this as part of chemistry. The next electron needs to occupy a different energy level, another orbital, if you will. And understanding this explains very much the way that the number of electrons, Z, in an element predicts its chemical properties. Columns in the periodic table correspond to electronic configurations with some similarity, which is why the affinities or the chemical behavior of these kinds of elements are the same. It also explains many, many other properties of the universe. We will meet the Pauli exclusion principle and some of its applications in what comes later. For the moment, I want to say what we need to understand from quantum mechanics is that we do have a picture of how atoms work. The description of a nucleus surrounded by electrons is fine if you remember that describing the electrons as actually orbiting is kind of a fudge. You should think of them as quantum particles described by a wave function, and that light, which is very definitely a wave phenomenon, is, under some circumstances, in particular when interacting with matter, described as a stream of particles, photons, and the frequency of a photon determines the energy of each of these light quanta through this wonderful Planck formula, E equals to hf. That is most of the quantum mechanics we will need.